Hello guys, welcome to my channel, and this is my lecture number 2, which deals with transient analysis of RL and RC series circuits under DC excitation. In the last lecture I had given a small introduction about power electronics, and in the end I also told you that transient analysis is very important to understand the working of a power electronics converters, because at the end of the power electronics converters there are some loads. It may be a resistive load, it may be RL load, it may be RC load, it may be a RLE load, where E stands for EMF. Hence it is very important to know the behavior of inductor and capacitor when it is given a DC supply. That is what we are going to study now. So let us start by taking a RL series circuit. Below the heading RL series circuit, I have drawn the diagram of it, which consists of a DC source Vs, a switch which can be connected in 2 points A and B. It is generally called a single pole double throw switch. Since it can be connected at 2 points, it is called double throw, and one pole which is indicated by point S. So it's a single pole double throw switch, and the load connected is RL. And on the right hand side, I have drawn two diagrams. One, the Vs, which is a DC source connected directly to the inductor, and secondly, in the second figure on the right hand side, the DC source is connected directly to a capacitor. So we'll study the right hand figure first, then we'll go in studying the RL series circuit. Now let me explain to you what happens when an inductor is directly connected to DC. If you compare the figure on the right hand side and the left hand side, you will see that on the left hand side figure there is a switch. Through the switch, once the switch will be connected to position A when Vs will be supplying the energy to the load, and once my switch is connected to B when Vs is not connected. So we are not applying Vs constantly to the load, which is RL. But if you compare the right hand figure, Vs is directly connected to S. There is no switch. There is direct connection between source and inductor. So Vs is appearing across the inductor for a long time. You can't remove Vs as in the left hand figure. Like if it is goes to switch moves to position B, Vs will be removed. So in the right hand figure, Vs can't be removed. It will be constantly applied across inductor. So I can say the circuit will reach steady state. So what my aim is now to find out the steady state values of inductor voltage and inductor current. Hence, what I have written in point number A is the impedance offered by the circuit. You know the impedance offered by the circuit will be Z, which is nothing but XL. XL is nothing but 2 pi FL, and since the DC voltage has a frequency 0, 2 pi FL will also be 0. Thus Z is equal to 0. Hence the circuit offers 0 impedance. If the impedance is 0, then what will be the voltage? You know V is equal to I into Z, that is written in point number 2. So V0 is equal to VL is equal to I into Z is equal to 0. Now point number C, what will be the IL, current flowing through the inductor? IL is equal to VL by Z, and since Z is equal to 0, IL will be infinite. Hence, from point number B and point number C, you can observe that VL is equal to 0 and IL is equal to infinity when the circuit is at steady state. This is the condition of the inductor. So from this you can take a conclusion. In which circuit does a voltage become 0 and current becomes infinite? So in we short circuit 2 points, obviously the voltage between 2 points will be 0 and current will flow infinite. Thus point number D addresses to it. That's why I had written at steady state inductor acts as short circuit because of the values found by me in B and C. Again, if you observe point number E, VL is given by LdIL by dt, which you already know it. Now VL, you have observed it to be coming out to be 0. How will VL be 0 if this equation is followed? L is a constant value, so L can't be 0. Obviously IL should be constant, because differentiation of a constant is 0, you know. So dIL by dt will be 0. So from here we'll reach a conclusion that inductor doesn't allow change in current. It tries to keep the current IL constant for some amount of time. Hence, two conclusions we have reached from here. Inductor at steady state operates at short circuit, and inductor has the property of not allowing change in current for some amount of time. Now we'll take the same circuit and replace the inductor by a capacitor. And since the voltage Vs, which is a DC supply, is connected always across the capacitor, so we'll assume that the circuit will reach steady state, and at steady state we will try to calculate the values of Vc and Ic, which is the voltage across the capacitor and the current through the capacitor respectively. We will be following the same steps as we had applied in a L circuit, which was connected directly to the DC. So first step was finding out the impedance, which is Z. Over here Z will be equal to Xc as showed in point number A. So Xc is nothing but 1 by 2 pi Fc, and since frequency is 0, Xc will be infinite, so Z will be infinite. So from if Z is infinite, we'll jump to point C first. We can obviously say Ic is equal to 0 without even writing the equation, because impedance is infinite, so current flowing through the circuit will be 0. Then jumping into point 2, without looking at what is written over there, can we make an idea from point number A and see what will be the voltage across the capacitor? Yes, obviously, as the current through the capacitor is 0, that means the capacitor is acting as open circuit. So if the 2 points of the capacitor is open, what will be the voltage appearing across the capacitor? It will be nothing but the supply voltage, which is Vs. So Vc will be equal to Vs, which is the maximum voltage of the circuit, or we can call it as open circuit voltage. So Vc is maximum because it is becoming open circuit and current is 0. So from B and C we will reach a conclusion. Since voltage is maximum and current is 0, capacitor at steady state acts as open circuit. So that is written in point number D. Again, if you write the current equation through a capacitor, Ic is equal to C dVc by dt. We had already calculated in point C, Ic is equal to 0. So if Ic is 0, C can't be 0 according to the equation, but your Vc has to be constant, so that differentiation of a constant becomes 0. So Vc is a constant voltage, and you had already observed in point number B. So Vc is equal to Vs. It's a constant voltage. As Vs is DC, so it will be constant. So dVc by dt will be 0 and Ic will be 0. Hence, we will conclude that the capacitor doesn't allow change in voltage for a small amount of time. Thus, from this circuit, we have two facts to remember. One, the capacitor will always act as open circuit at steady state. And the second one, capacitor does not allow change in voltage. Remember, inductor and capacitor are dual of each other. Why I am saying that? If you observe the equation number E for both cases, you will see over here Ic is equal to C dVc by dt. Similarly, the point number E of your inductor was VL is equal to L dIL by dt. So what is the current equation of a capacitor gives you your voltage equation of a inductor. So they are generally called as dual of each other. Hence you can remember it like this. If capacitor is open circuit on steady state, what is the opposite of open circuit? Short circuit. So inductor will be short circuit at steady state.
So let's start with the transient analysis of RL series circuit. Here in this circuit there is a switch which once gets connected to A and the second time it gets connected to B. So there are two modes of study. First, what we are analyzing is when switch is connected to A. So if switch gets connected to A, my Vs source gets connected to the load, that is RL load, through the switch and completes the circuit. So there is a closed path for the current to flow. That current we are naming it as IT. If you apply KVL over here, what you will get? KVL Vs is equal to R into IT plus L dit by dt. Now this is the first order differential equation, as there is d by dt, and we need to find the solution for that. So that's why here you can see I have written a first order differential equation, which is dy by dt plus py is equal to q. And you know a first order differential equation solution is given by y is equal to q by p plus k e to the power minus pt. This is very important. You should remember this. You can solve many equations that come in gate through this solution. So first order differential equation solution is very important in electrical engineering for any subject. Okay. Now I'll compare this with that equation. So this part is the dy by dt part. This is my py. This is my q. Rearranging these equations and writing in that form. If you observe that equation over there, dy by dt coefficient is 1. But over here dy by dt coefficient is L. So I'll take L common. So we'll get dit by dt plus R by L it is equal to Vs by L. So from here compare it with the solution. So dy by dt, that means dit by dt. So y becomes it. So writing the solution, y is equal to it. Instead of y, I have written it. Q by p, identify the p and q in this equation. Q is on the right hand side of the equal to sign. So Vs by L. P is R by L. So Vs by L by R by L gives you Vs by R. So Vs by R. Q by P got plus K e to the power minus Pt. What is P? P is nothing but R by L. So minus R by L t. So this is the solution for the equation of the current flowing through this circuit. But we need to find this constant of proportionality K. What will be its value? By substituting initial conditions. What is initial condition? Now remember. Now, consider inductor to be uncharged. So, if inductor is uncharged, that means current through the inductor is 0. And as you know from the previous study what we did, inductor doesn't allow change in current for a certain amount of time. So, from getting charged from its uncharged condition, its current will remain 0 for some amount of time. Then it will get charged to some value. So, if I consider the uncharged condition as some 0 minus condition which has occurred beforehand is equal to the present condition, that is I0 plus will be equal, because inductor doesn't allow change in current for the some instant of time, is equal to 0. This becomes my initial condition. Now substitute that initial condition in this it. What you will get? It is nothing but at t equal to 0 plus, which is my present condition. This equation is present condition. So it 0 plus. So I 0 plus is equal to Vs by R. Vs by R plus K e to the power minus R by t. T is nothing but 0. So K e to the power 0. So I 0 plus is 0 is equal to Vs by R. E to the power 0 is 1. So plus K, and K comes out to be minus Vs by R. So from here substitute the value of K over here. So it is equal to Vs by R minus Vs by R e to the power minus R by L t. So you take Vs by R common, 1 minus e to the power minus R by L t. This will be your equation for it. Since this is a series circuit, whatever current will flow through the circuit will flow through both resistor and the inductor. So this is nothing but you can write this as IL T also. Now if you are plotting this IL as I have shown over here, what you will do? This is the exponential equation, e to the power something. Now e to the power minus x, what does it mean? It is a decreasing function, and 1 minus decreasing means increasing. So basically this is an increasing function with maximum value how much? Vs by r. Why I am saying that? How will you get the maximum value over here? You can equate this to 0. Okay, so if you equate this to 0, your maximum value will be Vs by r, that is t is equal to infinite. So Vs by r is my it, which is the maximum value, and exponential form increasing. So I have drawn it exponential form increasing, up to which point it will increase? Vs by r. Now think about the things which we had learned when a pure inductor was connected to DC. What happens at steady state? It becomes short circuit. So when it becomes short circuit in this circuit, if this is short circuit, what is the current flowing through the circuit? Is Vs by r. That means at this point, when it reaches, it is reaching steady state. So you can understand why we have taught that inductor is short circuit in steady state. So you can explain it in this way also. Okay, maximum value is Vs by r, and how can a current Vs by r flow in this circuit? When my inductor will be short circuit. So inductor at steady state is short circuit. Now if you calculate VLT, so L DIL dt. I am not doing the differentiation, you can do it on your own. So you will get V e to the power minus r by L t. Okay, so if you plot this, what is the function over here? Again exponential, but decreasing, because e to the power minus ax. Okay, so a decreasing function with maximum value how much? V. So it's starting from V point and decreasing to 0 over here, exponentially decreasing function. Now at this point it has reached steady state. So what will happen? Current is maximum and voltage will be minimum, that is 0. See, at this point voltage is reaching 0. So this is the operation of RL circuit when my switch is connected to A. Okay, next we'll do when switch is connected to B and complete this figure IL and Vm. Now next, my switch is connected to position B. When my switch is connected to position B, my source get detached. So my inductor was previously charged. So my inductor now acts as a source. It will drive the current through this closed path. Now if I apply KVL, okay, so Vs is 0, so left hand side becomes 0. RIT, the same way as we have written it earlier, plus LVIT by dt. Compare it with the first order differential equation. Again you will see you have to take L common, So what you will write? DIT by dt plus R by L IT is equal to 0. Now writing the solution, how will you write? IT is equal to Q by T. See, Q is 0, so Q by T will be 0. K e to the power minus R by L T. Now we have to substitute initial conditions like the last case. Before it was getting connected to position B, my switch was in position A. So the value of current which was flowing through the inductor at position A becomes the initial condition for the current flowing through RL load when switch is at position B. Now if you look at the diagram, IL has increased and stopped at which point? Vs by R. So I can say that if my circuit has reached steady state where S was connected to A, my current that was flowing through the network is Vs by R. So Vs by R was the last position or last value of the current that was flowing when S was connected to A. So the last value of the last position becomes the initial value of the present position. So what we will write? I0 minus is equal to I0 plus is equal to Vs by R. Same concept. Inductor doesn't allow change in current. So previous current and present current will be same for a certain amount of time, for a certain instant. So previous current was stopped at Vs by R. Present current also will start from Vs by R. So I0 plus will be Vs by R. That is my initial condition. Again substituting it out here. So that is I0 plus. What is I0 plus? Vs by R. So Vs by R is equal to k e to the power 0. Again t is equal to 0 because it is the start of the new cycle. So k becomes Vs by R. So substitute over here. So what you will get? It is equal to Vs by R e to the power minus R by L t. K is substituted. Now you draw that equation. What will be it? It is nothing, the current flowing through L. So it is nothing but IL. Now if you draw this over there, e to the power minus ax, as we have told earlier, it will be exponentially decreasing. From which point it will decrease? From its maximum value, which is nothing but Vs by R. So my graph will continue from here, exponentially decrease to 0 at the end of the cycle. So this is my IL graph over here. Next, VL. What will be VL? Is equal to L dit by dt. Again differentiation you can do it. You will get over here minus d e to the power minus R by L t. Now again it is a exponentially decreasing curve. But from which value? Maximum value will be minus v. So minus v. It's starting from minus v now. It's starting from minus v now. And exponentially decreasing to 0. Okay. So, two conclusions we have to make from here. Very important conclusions. Which are, number one, the inductor current cannot be negative. Inductor current is always positive. This is a charging curve. When it was connected to the source, inductor was charging. Now inductor is discharging through the resistor to ground. This is ground over here. So inductor current during positive charging and discharging is positive. So inductor current is always positive. Is always positive. Second, very important conclusion. This we will be using while studying power electronics converter. That's why you should remember some conclusions very methodically. Okay. This is one very important. Next, from the inductor voltage, can I say that the average value of the inductor voltage is 0? Because this area and this area is same. Okay. If you consider a sine wave like this, if you take full cycle average value, what it comes? Average comes out to be 0. Similarly, positive and negative cycle over here is equal. So what will be the average value? 0. So average inductor voltage is 0 always. So this from here it gives volt second balance, that is integration of V dot dt is equal to 0 over an entire cycle. Okay, understood? So very important, inductor current can not be negative, it is always positive. Average inductor voltage is always 0. From there we are finding a volt second balance formula, which is integration of V over dt will come out to be 0, because the area of the positive and negative part is always same. So average value of inductor voltage is always 0. Why I have written this? This equation or amp, and this is called as volt second. This is voltage, right? and this is second, so volt second balance. This volt second balance equation is used for finding out the input output voltage relationship in power electronics converters. That's why I am telling you this one. Okay. So remember this, how will my IL look like, how will my VL look like, it will be exponential. Remember these 2 points. Remember another thing, that inductor is short circuit at steady state, capacitor is open circuit at steady state. These are very important points which you should remember. And this also the first order differential equation formula. Okay.
Now, the second is RC series circuit. I leave this circuit up to you to do a self-study, as because I'm addressing the third year undergraduate course, and this part, transient analysis, is a part of your second year circuit theory and network subject. You might have done all these things. But since I've taken up this topic, I'll just give you some relevant points to understand this RC series circuit also. So if you compare with the RL circuit and RC series circuit, what is the first difference? Your L is replaced by a capacitor C. Rest all circuit remains same. Operation of the circuit will be again same. One switch will be connected to A, then we'll apply KVL and find the equation of IT, and then switch will be connected to B, then we'll apply KVL and find the equation of IT. What the difference is? Please note down. I have written all the differences over here. Similar things you can find out easily. But what is the difference? Generally, capacitor stores some charge. So, whenever we are calling a capacitor to be uncharged, it is represented by voltage across a capacitor. So, initial condition of capacitor is given by voltage. Hence, we have written Vc0 minus is equal to Vc0 plus is equal to 0. As we know that capacitor doesn't allow change in voltage, hence for a small instant of time, even after switching occurs, the voltage will remain same. So capacitor uncharged means voltage 0, whereas inductor uncharged means current 0. Then this initial condition you put in the KVL and find the value of K. Likewise we had found in RL circuit. I had also told you that capacitor is a dual of an inductor, right? Now you can observe in the third column, first diagram or first figure is of Vc. If you recall the figure of RL series circuit, the first figure, that same figure was of IL, current flowing through the inductor, but that same figure now becomes of the voltage across inductor, because they are dual of each other, as I told you. So the second figure on the right hand column or the rightmost column for the inductor was voltage across inductor. Now this becomes current through the capacitor. Maximum values all remain same, Vs by R. Hence we can come up to two conclusions from this figure, as we had come up in RL series circuit. So from the second figure of which states which we are seeing as IC, we can say average current through the capacitor is 0. So it will give amp second balance equation. Integration of I dt over the entire circle is 0. This amp second balance is generally used for finding out input output current relationships in a power electronics converter. On the rightmost column, the first figure is of Vc. So we can write a conclusion that voltage across the capacitor is always positive. So again, if you compare these 2 points which are written in the middle column with for a RL circuit, in the RL circuit average voltage across the inductor was 0, but over here same thing applies for current. Over here in the second point, voltage across capacitor is always positive, but for an inductor current is always positive. So you solve this circuit by keeping switches at A and then switch it at B. I think you can do it like the last thing. First order differential equation, solution is given, you will get these two curves. This is very important for you to understand the operation of RL and RC and how the waveforms look like of VL, VC, IL, IC under DC excitation. So hello guys, I have come to the end of lecture number 2. Hopefully you have understood the behavior of RL and RC series circuit under DC transients, and I have told you to remember some of the conclusions which will be very important as we'll be applying those conclusions while studying the power electronics converters. If you have any doubt, please let me know in the comment section. And if you want any other separate topic to be explained as out of this lecture or the subject which I am teaching, please let me know. I'll try to give my best to explain that in a different lecture, obviously. Okay. So what will be the content of my lecture number 3? I'll be starting on with a non-isolated DC to DC converters. These DC to DC converters are of 3 types. One is step down converter, second one is step up converter, third one is step up down converter. So according to the name only, you can find out how or what does it do. Step down converter, what does it does? So it's a DC to DC converter. So if you give a 15 volt DC, you should get a 14 volt at the output, or at 1 volt at the output, or 6 volt at the output. So it is step down converter. If you take a step up, so it can step up from 14 volt to 20 volt, etc., etc. And step up down, in the same converter we can up or down the voltage, and we'll see the operation, how it operates. So next class we'll start on with buck converter in complete detail. In your gate, questions comes from this buck boost converter, or step up down converter. So it is very important for you to understand, and also some formulas are to be derived for these converters which will be used for solving problems.